right, so day 2 of 6-1 for calculus, which is, again, slope fields. You may notice today's a little different already, that I gave you the slope field, and now we're actually going to try and use that slope field to kind of find out, well, what would the original look like? And again, that's what slope fields are for. And then also, well, maybe we want which particular one we want. Okay? And so we take a look at this first one. And the technique we're going to use today is actually called separation of variables. It can get a little harder than the one we're looking at now. What we're really going to do is on one side of the equation, we want everything dealing with one variable. And then on the other side, we want everything dealing with the other variable. So really the tricky part is everything over here appears to be pretty much dealing with x, except this isn't over there. And that deals with x as well. And then here's a y and an x then right now, so it has 2 variables. So we have to figure out some way of getting that out of here. And really that does mean, dy divided by dx. So a very simple way of getting that over there is to multiply both sides by dx, so that cancels. And then so this whole side is dx. So the nice thing is basically what we have. Leave yourself a little bit of room here, and then start writing secant squared plus 2x plus 5. And maybe you're wondering why I said, well, leave yourself a little bit of room. Obviously, you're going to put something there. Now, if I want to get back to the original, I don't want to know dy, I don't want dx, and so what we're going to have to do is undo that. So we're undoing a derivative, which means antiderivative. Okay, so antiderivative of both sides. Well, this side here is the antiderivative of basically 1 dy, which is y, okay, equals. So now we have to go to that side, and now it's everything with respect to x. And remember, you can pretty much do each, seeing it's all addition there, you can do each one of them separately. Now, if it was multiplied there, then we'd maybe use our integration by parts or substitution or something along those lines. But we don't have any of that. Now, first, if we take the antiderivative of secant squared, you might not know that one right off the top of your head, but it is on that sheet I gave you. And so the antiderivative of secant squared, if you were to look it up, is tangent. And if we take the antiderivative of 2x, it's plus basically 2. You take it up a power x to the second over 2. And so in other words, x squared plus 5x plus some constant, because it could really be any constant there. So y cleaned up is tangent of x, whoops, plus x squared plus 5x plus some constant. So in other words, that's what the original, like if I went to graph that, which I'm going to actually show you a graph here in a second. If I went to graph that, I know it would look like one of these patterns here. It all depends on what I choose for the constant. And remember when we did transformations of graphs, if you just add or subtract something at the end, it pretty much just moves your graph up or down. Okay, it just is all it really does. And so perhaps if I choose a particular constant value, it might end up looking more kind of like that. That's kind of what it looks like, at least for these values, right? And this appears to be negative 2 to 2 for x values, right? And so if I were to look in there, it might look something like that. So we might, very strangely, end up with something that looks somewhat cubic, okay, depending on what constant we have, at least for these values, because that's all I had you do the slope field, or showed you the slope field for. If we go beyond negative 2 and 2, who knows what happens? We'd have to go and do it and find out. And so here, basically, again, what you did is you separated the variables. I got all the y's on one side, all the x's on the other, and then I did the problem. Again, this is a pretty simple separation of variables. And so what I'm going to do now is I'm going to erase this stuff, and I'm going to show you a graph that I actually made, and then you tell me what I chose for a constant. See if you can figure out which of these options, which of these paths did I choose as far as my constant is concerned. And the reason I have to erase it is because I have it right here. Okay, so that's a very complicated graph, and at first you would say, well, that doesn't look at all like what we have over here in the slope field. Well, I think the main problem is over here it looks like I went maybe negative 10 to 10 as my x values, right? So if you find negative 2, well, that's right about here, right? Positive 2, well, now here's that cubic that we are kind of seeing over here. So you notice if we went further with our slope field, we'd have this crazy stuff happening over here. We'd have this weird stuff happening here. A bunch of asymptotes all over the place. Because again, sometimes tangent is undefined. And that would be our biggest problem on that other one, that tangent sometimes you can't do, because remember that's sine over cosine. So over cosine is 0, we would have a problem. And so here, yeah, we're looking at this. Oh yeah, it does match. So which of these constants did I choose? Well, it appears as though I chose, of the ones I see, I chose the one that pretty much went through here. So the constant I chose was 0. Okay, I chose the easiest one. Okay. So any questions on that? Again, you could go to your graphing calculator and put a bunch of different constants in. I showed you how to do that kind of earlier in the chapter. And so you could do that if you wanted to, and all it would do is get really confusing really fast because it would throw a lot of these graphs right on top of itself. So, and it would just move stuff up or down. Okay. And so you don't necessarily need to do that. Okay. So that's one separation of variables problem to get it back to the original. And here we have another one. Again, I've given you the slope field. So we kind of know about what it's going to look like. I would say in general, if I tried to follow one of these paths, maybe I'll take this one. It goes down, and somewhere it comes back up. And then somewhere it goes back down, and then somewhere apparently maybe it straightens out, or maybe it comes back. I don't know. We'd have to kind of figure that out. But that's in general probably what it's going to look like. Again, it all depends on what constant. Now this time I didn't leave that constant out there. What I've done is I've given you the derivative, and I've also given you a point that the original has to go through. I've basically specified that the original has to go through 1, 0. So if you think about it, I'm going to do the one that goes through here. So you can kind of trace that path and kind of figure out about maybe what it's going to look like. But again, at the end, we're not really sure. Is it just coming down straighter, or did it somehow change direction in there? You know, there's a lot of things that could have happened, and we got to kind of figure out what the original is so we can find out. And so once again, we are going to separate variables by simply multiplying both sides by dx, because you notice that everything's x over here, everything's y over here. So again, I'd leave myself a little bit of space. I didn't leave myself very much, because to get rid of this, I have to antiderivative, because that's a derivative. And so again, this is 1 dy if you want to look at it that way, so it's 1. And then I can do these separately, because again, it's just a constant, the 6 times x squared, so that's fine. And here it's just 1 times e to the x, so it's no function times a function. That's a non-constant function, I guess you could say. And so I can do them separately. And so we take the antiderivative of e to the x, which is quite simply e to the x. That's a good one. And then we take the antiderivative of this, which hopefully you're getting kind of good at these. So 6x to the third over 3, right? And we're going to still have to put plus a constant because it is still an indefinite antiderivative or integral. Okay, so if we clean this up a little bit, we get y equals e to the x. Okay, this does cancel. This goes in there once, twice. So what, minus 2x to the third plus some constant. Okay. So now to find exactly which one, well, yeah, we know it goes through this point. Well, that's great, but still we don't necessarily know what the function looks like. But we do know if I plug or substitute 1 in for x, I better get a result of 0 for y. So what we can actually do is actually do that. Put 0 where y was, and wherever we see an x, put 1. So minus 2, so here's another x, so I have to put, once again, 1. And then you notice when you do that, I know it looks like e is a variable, but remember, e is a number, about 2.71828, blah, blah, blah. But what we're really looking for here is the variable in this problem, which is c, the thing that can actually vary. Okay? And obviously we can see by our slope field that it could vary a lot. It could be a lot of different things. Again, it's in this position, though, that it would just move this up or down. Okay? So now let's just go ahead and solve this. So basically, I don't know how you want to do this. We'll go slow, I suppose. So it's e. This is minus, well, 1 to the third is 1, so minus 2 plus a constant. So if I want to get the constant by itself, basically the e and the negative 2 have to go to the other side. And so to take care of that, I would probably subtract e and add 2. That looks like a c, sorry about that. So if I subtract e and add 2 to this side, I find out my constant is basically negative e plus 2. And so then what's the answer? Is negative e plus 2, is that what this graph is? Well, no, that's the constant of this graph. And I would leave it that way because that's more accurate. Okay, I could get a decimal, right? It'd be negative 0.1828, something like that, right? 71828. But what we're going to do is actually take this information and substitute it into everything else I know, which is right there. So to get this final answer, and you can write it many different ways, but you can write it as, you know, I can probably get rid of the plus if I want to write it that way. We can write negative e plus 2 is our constant. And what some people I've seen do in the past is kind of focus on making sure they know that that's the constant. Or you could write 2 minus e. It all works fine. And so this right here, if you were to graph that function, would be the function that has the combination of that as a derivative, and it goes through that point. So it's going to be the one that definitely hits that point when we go and graph it. And once again, I'm just going to erase some of this stuff, but I'll give you a second here to write it down if any of that was confusing. And then I do have the graph kind of in the background again. And we'll have to kind of, again, look, well, this one over here goes from -1 to 2, and so you got to be careful, what am I looking at in my graph so that my slope field actually makes sense. So there you go. Let's get rid of some of this stuff. There we go. And I'm pretty sure it's in the background there somewhere. Maybe not. There it is. Really small. So this one looks like it went out maybe just a little bit further, although this, if you look up here, this does appear to be -1, and here's +1, and here's probably +2. It's kind of out on the outskirts there, right? -2 over there. And so I would say there's your 1, 0, right? It's following through. And so let's see if that makes sense with what we have here. Yep, it went along somewhere. See, part way, because here's 1, right? Part way, it kind of changed direction, so that matches. And then somewhere along over here, well, actually, I should hit it a little higher. Sorry about that. Okay. So it hits a little higher, and somewhere over here, it changes direction and takes off. So you notice when you do it, it doesn't necessarily give you these values, right? But to find those values, I could set my derivative equal to 0, right? Well, my original, I could set this equal to 0 to find out where those places are, because that's your relative max, your relative min, right? And so that would find those things for you, okay? Where you have your horizontal tangents. Okay, that would take some work, but we can do that. Okay, we have ways of getting all of this information. So I see this graph that I made in red over here very much does resemble that graph over there. So it makes me believe that we probably have the correct equation, which was e to the x minus 2x to the third plus 2 minus e, or minus e plus 2, however you chose to write it. So hopefully you can see that slope fields can actually be helpful, because it will show you, oh yeah, okay, I probably went through this and did it properly, as long as you have the right slope field. And we're just going to check what this other page is for. Oh, this blank. All right, so if there's any questions, please feel free to ask. Otherwise, good luck.